On the previous slides, we demonstrated that if a function has the periodicity of the crystal, then the wave vectors that appear in its Fourier series expansion cannot be arbitrary. They must be reciprocal lattice vectors. So now let's examine the basic building blocks of that Fourier expansion, namely the functions e to the ig dot r, where g is the reciprocal lattice vector. The first important point is that e to the ig dot r has the same periodicity as the crystal. Why is that true? Let's translate the position by any direct lattice translation vector, capital R. Then we have the expression shown here. Because e to the ig dot capital R must be equal to 1, we immediately obtain this result. This means that e to the ig dot r is itself crystal periodic. This is a very important point because it shows that these functions are legitimate basis functions for expanding any physical quantity that has the same periodicity as the lattice. Now let's discuss the second important property, the integral of e to the ig dot r over 1 primitive cell volume. Based on the argument above, if we integrate e to the ig dot r plus capital R over the volume of 1 primitive cell, we immediately obtain this expression. Rearranging terms, we obtain this equation, which is true for all reciprocal lattice vectors. Now let's take a closer look at this integral itself. If g is not equal to 0, then the integral of e to the ig dot r over 1 primitive cell volume must vanish. On the other hand, if g equals 0, then the exponential is simply equal to 1. So the integral over the primitive cell is just the primitive cell volume, which is denoted by capital omega. This result says that the average of the plane wave e to the ig dot r over 1 primitive cell vanishes unless it is the constant function. Since for g is not equal to 0, the phase changes across the primitive cell and the oscillations cancel exactly over 1 period of the lattice. So the result can be written as shown in this equation. This is an orthogonality type result. It tells us that the average of any non-trivial reciprocal space plane wave over 1 primitive cell vanishes. Only the g equals 0 term survives. Please note that in this expression, the g vector may also be the difference between any two reciprocal lattice vectors. This immediately leads to an important interpretation, since the set of Fourier wave vectors must be the set of reciprocal lattice vectors. In the Fourier series expansion of any periodic function in the direct lattice, the set of functions e to the ig dot r forms a complete orthonormal set up to normalization for representing any function that has the same periodicity as the crystal. So the main message of this page is each e to the ig dot r is crystal periodic. These functions are mutually orthogonal over a primitive cell, and together they form the natural Fourier basis for periodic functions in a crystal. Now that we know the functions e to the ig dot r form an appropriate basis, let's derive the expression for the Fourier coefficients. Suppose we express a periodic function f of r by its Fourier series expansion as shown here. The question is, how do we determine the coefficient a sub g? So to extract one particular coefficient, we use the same strategy as in ordinary Fourier series. We multiply both sides of the equation by another basis function, which is e to the I g prime dot r, and then integrate over one primitive cell volume. We obtain the expression shown here, which after rearranging the order of integration and summation, we end up with the expression as shown. Applying the orthogonality relation from the previous page, we know that when g plus g prime equals 0, the integral equals the primitive cell volume, otherwise it must vanish. This means that since g runs over all reciprocal lattice vectors within a crystal, the integral is non-zero only if g equals minus g prime. We then arrive at the equation for a sub minus g prime as shown here. Equivalently, if we rename the index, we can write the coefficient more conventionally as shown in this equation, which we have replaced minus g prime with capital G. This result is extremely important in solid-state physics because many physically important crystal periodic quantities can be written in exactly this form. For example, the electron density, the crystal potential, the dielectric function in a periodic medium, and later even parts of Bloch wave descriptions. So the reciprocal lattice is not merely a geometric construction related to crystal planes. It is also the natural mathematical framework for expanding periodic functions in Fourier space.